All right, how's it going, everybody? Welcome here to week 6. And this week we are going to start with our introduction into continuous probability distributions, which is really kind of one of our somewhat more primary goals of this semester, as opposed to our discrete probability distributions. But we want to use those to kind of help us understand where we're going here. So we're going to look at some examples of discrete topics that we've already seen to help us understand exactly how those relate to the continuous topics of interest that are coming up here. This week, we are going to both introduce our continuous probability distributions as well as take our first test. You should have seen in Canvas that we've got some information regarding that test coming up here. In a typical week, I usually cover 3 or 4, or I think there's even one week this semester where we get 5 sections in there, I think, depending on the amount of content that's out there. This week, since we have our test, I'm only going to cover about half as much content here, so we're only going to get these 2 sections in this one video for this week. So this week, there's really just 2 sections that we're covering. There's only one video to watch, and none of this content that's going to be in this video, none of this is actually on the test. The test will just cover up to chapters 1 through 4. I think that we essentially wrapped up chapter 4 with 4.3. So that's the edge of the content associated with the test that we'll be taking on Wednesday. On Wednesday at noon, I will publish in Canvas a little module that will have the test available in it. So you'll be allowed to start the test if you'd like as soon as noon on Wednesday, and you will have until noon on Friday to have that test submitted to me. I'm just trying to space this out a little bit. I know that people have different schedules and stuff for things, so I just want it to be, if you just want to knock this test out the second that I post it, go for it. If you want to try and do it all on Wednesday night, go for it. Thursday night, go for it. Thursday morning, whatever. Honestly, not that I would encourage you to ever save things that are important until the last second, but even do Friday at noon, it wouldn't be unreasonable to just wake up on Friday and give yourself a few hours to take the test on Friday. It's not going to be outrageously long or outrageously difficult, is not my intention. So I'm trying to just give you some optional time slots to make sure that everybody has an available time that'll work for them to make that test happen there. So make sure that you're on top of it for the test. Don't forget, don't save it to the last second. All those standard things that you should do with tests about being responsible with test taking. So look alive for that stuff out there. So again, there's nothing in Canvas right now for the test because you can't see the test because I haven't posted it yet. But on Wednesday at noon, I will click the publish button and it will become available to you. And again, no video tomorrow, just the one today for this week. So what are we talking about here? We're going to get into chapter 5 here, our continuous probability distributions. And what we want to do is we want to look and see how do these compare to the discrete probability distributions that we've been discussing last week. We're going to obviously see some differences, but there's going to be some close relationships also where we're going to take a little bit of intuition from what we've already done and extend that to what we would now like to do. So where I typically always like to start with is let's start by talking about something that we already understand here. And here's one of the things that we did last week. Last week we asked the question, what is the probability distribution associated with rolling 2 dice? And what we did is we came up with a graph that basically looked like this. I stole this from the internet, but as you might be able to believe, there's about 1,000 different graphs on the internet of various probability distributions for very common things like rolling dice here. So this was not exactly difficult for me to find here. So we saw this graph. We saw this represents the individual probabilities of each of the outcomes that are associated with rolling dice. Is today not going to be a day that I'm allowed to type again here? Okay, seems fine. So now scroll. Okay, there we go. So again, our probability distribution that we came up with, and what we decided is that we should be able to answer questions that look like these guys, right? What's the probability that we roll a 5? What's the probability that we roll a number greater than 9? What's the probability that we roll a number between 2? Or notice, well, in particular here, notice the lack of or equals 2s in this one. We'll get to that in 1 second. But here's what I really want to actually emphasize for the day here. One thing that I like slightly less about this graph than the one that we made is that this graph here has actual frequency counts. It has the actual number of counts that we would expect to see if, for example, we were to roll a die the 36 times that are totally represented out here. If you were to add up this 1 plus 2 plus 3 plus 4 all around this guy here, we get to 36. So this is our actual frequencies. These are excuse me, these are like our expected frequencies if we were to roll the die 36 times. What I want to do is also add on a column over here instead. That should be our relative frequencies. This is what we did when we did this one last week, is our relative frequencies we knew were things like a 1 out of 36 and a 2 out of 36, etc. on up the row here. These are the proportions of responses that we expected to fall into these categories here. So these were our relative frequencies associated with each of these different outcomes here. We expect that on average, 6 out of 36 rolls of 2 dice will give us a sum of 7, stuff like that. So we can read that off of the table here. So this relative frequency column is going to be slightly more valuable for us in interpreting how this discrete stuff is related to our continuous stuff here. So what we want to see is that if we want to ask questions like what is the probability that x is equal to 5, then what we should notice here in this case is we are literally interested in discussing this rectangle right here, right? There's one rectangle that I am interested in, and it looks now all these rectangles obviously look the same when I just draw one standalone one right there. But here's the thing that I'm noticing. This column of 5 right here, this has a width, that the width of this rectangle right there is 1. I guess we can think of this as going from like 4.5 to 5.5 if we really want. We know that those half intermediary ones aren't super useful for dice roll thinking about things like that here, but the width of this rectangle is certainly 1. We just determined that if we're thinking in terms of relative frequencies, then the height of this triangle, so I've got a 1 and I've got a 4 over 36. And we should notice that the area of that rectangle is the length times the width. And here we're getting a 4 over 36 times 1. And that is just giving us 4 over 36. That is the probability that's associated with experiencing that event of a 5 right there. So I do think that one of the big takeaways that we should see with this guy here is that the area associated with that particular piece of our graph is exactly equal to the area or the probability of interest. We wanted to know about the probability of seeing 5, and what we instead did is we did some geometry right here, and I literally found the area of the rectangle that is associated with the outcome of 5, and the area was exactly the same thing as the probability right there, the 4 and 36 event that we had previously seen last week there. And we can do similar things here now. Now if I'm looking for the probability that x is greater than 9, note this is not greater than or equal to. If I'm going to get greater than a 9 when I roll the dice, that means that I am interested in 10, 11, and 12. Right? And so it looks to me here like I can then go ahead and consider this area here. This is really my area of interest now. I have those 3 parts of the histogram that are out there. And again, we could do an area computation here to determine the actual probability that's associated with this. Alternatively, we could see that we're really, in a sense, okay, let's just do this as our area here. This overall area should be the area of the first part plus the area of the second part plus the area of the third part, right? If this is A1, A2, A3. And we could find all these, right? This is going to be 3 out of 36 times 1 plus 2 out of 36 times 1 plus 1 out of 36 times 1. I can see here this is 3 36ths plus 2 36ths plus 1 36th should be giving us 6 36ths overall for our probability right here. And it is the case that there are 6 different ways to roll 10, 11, or 12 on a die out of the 36 total possible outcomes there. And so again, I'm kind of trying to emphasize here that the thing that was happening last week, but that we didn't just explicitly state, was that the areas of these histograms are exactly the probabilities of interest as long as our y-axis is the relative frequency rather than the actual counts associated with what we expect to see out there. So finally, we could do this one here, and this one I almost am more interested in this one just for the sake of rephrasing a probability statement here. You should notice in a discrete setting is if I need to be, x needs to be larger than 2, then 3 is really the smallest I can be. If x needs to be less than 5, then 4 is really the smallest I could ever be. So recognize that these two are equal to each other here with our less thans versus our less than or equal to's. If you're less than 5, then the first value that is acceptable is actually 4. So x is less than or equal to 4. So in this case right here, x is between 3 and 4. So here we are interested in this interval of values here for the third one. And again, I can kind of see things like we have a total height of 2 plus 3 is 5/36, a total width of 2 there. And so the heights here of one width of height 2 and a width of 1 of height 3 is going to give us a grand total of 5/36 out there for this guy as well. And again, we can do this geometrically, or we can do this inferring this is sort of like data from a table right here. In these cases, I don't think that we have a huge amount to gain by thinking about this geometrically and doing areas, because this is just as easy to do thinking about counts and just adding relative frequencies, partially because all the widths here are a width of 1 in between each of our chunks right here. But what you might be able to imagine for yourself is as we have more and more and more different outcomes that are available to us, it's going to become less and less reasonable for us to just add some numbers together. And so maybe this area idea is something that's going to be more useful to us in other settings here. So again, our key observation here is that as long as our y-axis is measuring relative frequency, the percentage or proportion, then the area is equal to the probability, right? That's our kind of our, if I'm going to say one sentence about all of section 5.1 and 5.2, it is the area is equal to the probability. That's our big idea here for our graphical representations of our probability distributions and computing probabilities that are associated with them here. So let's step this up now to thinking about a continuous setting here instead. In a continuous probability density function that we want to think about, we want to kind of see the graphs and see how our graphical ideas really relate to the same graphs that we just saw a second ago. What we want to realize is that when we are talking about discrete probability functions, like the ones that we just saw 1 second ago with the rolling of the dice, there is only a finite number of possible results. You can only get a 2 through 12 and whole numbers only, right? I can literally list the 11 possible outcomes that we could ever see here, 2 through 12 inclusive, whole numbers only. There's only 11 outcomes that could ever be experienced. There's nothing else that could ever happen there. So because there are a finite and really a manageably countable number of possible outcomes, it's simple for us to individually assign a probability associated with each one and call that our probability distribution. We can represent each of those probabilities as a single rectangle in a histogram, and the area of any chunk of the histogram, right, not just one rectangle, but maybe several rectangles, the area of any rectangles are going to always be proportional to the probability of experiencing that event of interest that's been spanned by those rectangles. So really, again, strongly we want to associate the concept of area of a graph with probability of an event. That's kind of our big, broad concept takeaway from this unit here. So, in contrast, in our continuous probability functions, such as the distribution of adult male heights, there is basically an infinite number of different responses that we can get. And I'm going to say here, it might be that it's better for us to think of this as an effectively infinite. If the number of different responses that we can get is too big for you to individually manage by hand, right? In our discrete setting a second ago, we had 11 possible outcomes. But if we're measuring height accurate to 2 or 3 decimal places, then immediately we're talking about thousands and thousands of different outcomes, and that's only limited by our precision of measurement. If we could measure super duper precisely to 10 decimal places of accuracy, then now we're talking about billions of different height measurements that we might be getting. And so technically, while a billion is not infinite and even 1,000 is not infinite, when we have a significant number of possible different outcomes where it doesn't make sense to individually categorize each one as its own outcome, this is where it's better for us to be considering our variables to be continuous variables here. So adult male height is one of those things where technically speaking, we could measure our heights down to the atom, and we could technically get how many atoms tall are you. And in a technical sense, we could think about that as a discrete distribution since there is a whole number of atoms that you always have to be. But that's not really an effective way for us to think about that variable because if there are billions of different atoms high that a person could be, it's very difficult for us to meaningfully assign individual probabilities to each of those billions of events out there. So when I say effectively infinite, I mean it's there's nothing that humans can measure with infinite precision, basically. And so in a lot of cases, we are helped by thinking of variables being continuous, even if we don't personally have the machinery to measure it with infinite accuracy here. So that was my long-winded way of saying we should think of things as height and as age as having an infinite number of responses, even though humans are technically limited in our sense to measure those things. Our age is changing constantly. Every second that passes, you're a different age than you were before. And honestly, height probably changes in a very similar way, right? We're always we get a little bit taller at night, we get shorter during the day when we stand up more, stuff like that. So if this were the case, then we would have a histogram, if we wanted to think of it as being discrete, that would have an infinite number of bars. Again, it's not very feasible for us to directly manage here. It's still the case that the area of interest in the graph is equal to the probability associated with seeing those events. And since the probability of seeing any one of our possible outcomes is 100%, this is like saying, what's the probability that you roll between a 2 and a 12 for your sum on two six-sided dice? Well, there's a 100% chance that you will. There's no outcomes other than that, right? So since all outcomes collectively we would represent as 100% of all possible outcomes, that means that the area underneath the entire probability distribution function should always be 1 to represent 100% of the area. So the series of graphs here that I have is we can think about breaking our things down into more and more different breakdowns, right? This would be like saying maybe tell me what height you are, but only tell me accurate to within a whole inch. Then maybe say now tell me accurate to within a half inch. Now tell me accurate to within a quarter inch. And as we get finer and finer and finer with our measurement, then we get something that looks a little bit more like a smooth continuous curve rather than a chunky, blocky histogram like we're seeing over here. You should notice that when I asked this question, the way that I verbalized that example, I don't even have that written right here, but the way that I just verbalized this was as perhaps we can think of this leftmost graph as how many inches. This is how many half inches tall are you. This is how many quarter inches tall are you. You should notice that in this first case, if I ask how many inches tall are you, that's asking you for a count of the number of inches tall that you are. That is a counting of inches. On the other hand, once we get over to here, if we're talking about things of saying like, report to me your height accurate to 1/10 of an inch, that is a measurement of our height rather than a count of the number of inches. And that's a very technical difference. I certainly can't think of trying to identify any true definition to that distinction right there. But think about the difference between counting something and measuring something. If you're counting something, it's guaranteed that you have a whole number value of something, and that's often going to put us in our discrete setting. If you are measuring something, then one of the questions we should be asking is, well, how precisely should I measure it? To the quarter of an inch, to a tenth of an inch, to a hundredth of an inch? And once we get into discussions about precision, then that should be an indicator to you that we're thinking continuous probability functions here. So these graphs should kind of help you see how we can, in a sense, progress, in a sense, from a discrete to a continuous probability distribution by taking more and more finer samples from our more precise measurements from each member of the sample, rather than taking rougher values here that lump everybody into groups. So a graph of a PDF, a graph of the probability distribution of a discrete random variable, is a histogram. It has distinct bars for each of their own outcomes with their own areas representing the probability of a given event. That's all this stuff right here. This is our discrete outcomes, and even this one over here on the right, even though this is getting very, very close to being more sensibly a continuous graph right there, we can see the individual bars and the height of each of the bars, and we can compute the individual areas of rectangles. On the other hand, the graph of the PDF of a continuous random variable is going to be a smooth curve. Okay, not technically, it doesn't have to be smooth. I'd like to think of them as smooth curves. Some of them might have a corner in them instead of a smooth curve. That's a technicality for several semesters from now, don't worry about that. So think of our PDF of our continuous random variable being graphed as a curve instead of as like a histogram, where the area underneath the curve between values of interest still represents the probability. We're still taking with us this concept that the area graphically is equal to the probability of experiencing the event that's being described in the graph. So let's take a look at some examples of these. I've got a couple examples here to lay out kind of how we should be thinking about these continuous probability distributions today. And so what we'll start with is thinking about home prices in San Francisco. So here we have a graph that's been provided for us by the Urban Institute. And what it is doing is it's giving us two graphs of the distribution of home sale prices in San Francisco, once in 2007, once in 2017. So some things that you can see here are, we certainly do have dollar amounts that are described on our x-axis. You should immediately be shaking your fist at the creator of this graph for not having indicated a y-axis over here. We don't have any measurements over here. But here's the thing that I know. Because this is trying to describe to us a probability distribution, what I know is that the area underneath this blue curve here is overall 1. This is saying 100% of all home prices in San Francisco have been accounted for. Similarly, the yellow one, our lower one right here, our 2017 graph, this is representing 100% of all homes in 2017. So the overall area underneath the entire thing here is 1. And so it might be the case that we need to stop and think about scaling of our graphs. What is the appropriate y-axis measurement over here to result in us having this area of 1? Well, that's something that we'd have to kind of consider. We're going to have to kind of work out some of our difficulties with these areas here. We're going to talk about that quite a bit. So just to kind of get us started here, like what kind of questions am I even asking here? And the first question that I want to ask here is, graphically, and just in our graph here, determine the region that represents the probability that a randomly selected home in San Francisco in 2007 is worth between $1.5 million and $2 million. Right? So I want to come back up here and remind myself, I know that I'm interested in a 2007 home. I've really got two different continuous probability distributions here. The 2007s are the blue right here. So I'm noticing here, and by the way, let's very briefly talk about our home prices here. It looks like in 2007, San Francisco had a vast majority of its homes were worth in this $500,000 to $1 million range. A huge chunk of them were very consistently in the $500,000 to $1 million range. And it does look like there were a bunch of nicer homes out here. As we know about home prices, it's really hard to have extra cheap homes, but it's kind of easy to have really expensive houses out there, right? It's really hard, especially in San Francisco, to have like a $50,000 home. But there's no shortage of $2 million homes out there in San Francisco, I'm sure, especially today. So what we can see has happened over time now as we're moving into 2017 is it looks like this curve has spread out a little bit more. We don't have such a drastic peak up there. It also looks like the peak has moved a little bit. It looks like the most common home prices has increased. It looks like we're now in the range of like $750,000 to $1.25 million is now the more typical range right there. Maybe more centered at 1 million, rather centered at like, I don't know, like 600,000 out there. It also looks like things have spread out. It looks like there's now a broader spread of home prices in San Francisco. It now looks like in the past, there used to be most homes fell into a certain age category. It now seems like there is a much broader spread of different home values that are in San Francisco now as opposed to 10 years ago, or if I'm thinking of now as 2017. So back to our question here. We identified that 2007 is our blue curve. So I'm looking at the blue curve for our question here. And I want to just represent on the graph, where do we see the region that represents the probability that our selected home in San Francisco is worth between 1.5 and 2 million. So I'm just going to come over to where I about see my 1.5 amount right here. I know I'm on my blue graph, so I'm just going to only indicate this on the blue parts. And on the blue graph right here, I could indicate my region of interest here. And I'll just shade this guy with some diagonal lines right there. So what we're kind of suggesting here is, given that the entire area underneath the blue curve is 1, however much area is in this particular region of interest right here, that shaded region of interest, that is exactly the probability that we would identify a randomly selected house to be worth between 1.5 and $2 million out here. So the point of this question is just to say, interpret the area of a graph as a probability. Now, immediately what you should be realizing is we have no real sensible way to actually find this area right now. This is obviously our challenge right here. But I'm just trying to get our graphical concept down that area underneath a curve between two values of interest is literally equal to the probability of experiencing that event. given that our y-axis is measuring our relative frequencies of events. Here we weren't given a relative act or a y-axis of relative frequencies, but you should notice even if we were, this is an awfully awkward little shape right there that graph is taken on right there. I think it would be a little difficult for us to measure these. So we're going to have to talk about how are we actually going to get a probability measurement here, but at least I can indicate on my graph what area is the area of interest. And I can see here, by the way, this represents a pretty dang small chunk. I would have to estimate this to be, I don't know, 5 to 10% at best of the area here. I think even 10% is a little much right here. A huge amount of our areas is packed up right here for the blue curve. So I don't know. I think maybe actually more like maybe like 3 to 6% is probably a little bit more like what we're looking at in that guy right there. So we could at least maybe make an area estimate right there, a proportion estimate. So that's all I wanted to look at here. This is a bit of a difficult graph to read, but it's a nice smooth curve. It's talking about home prices in San Francisco, a thing we can understand here. So let's go ahead and look at a graph and see some more technicalities of some probability computations. This one will be a little bit more directly relevant to where we're going this semester. In example 2 here, we're going to think about adult male height. This is an example that I bring up very regularly here. Adult male height is something that's nice to talk about because it is normally distributed. There is an average. You are equally likely to be above average height as you are below average height. We are symmetric on the left and right hand sides. And this does follow a very nice and well-studied probability distribution, the normal distribution. In our case here, I have given you the graph of the standard normal distribution. When we say the standard normal distribution, that means that we're going to have an average of 0. You can see that we are centered at 0. We are going to have a standard deviation of 1. We're going to talk about how to interpret the standard deviation very specifically. That'll be exactly what we do next week. Next week in chapter 6, we'll begin talking with the whole reason we're covering continuous probability distributions in general right now is just so that next week we can talk about the normal distribution, which is probably the most important continuous distribution to know about. So on this graph, I want to do a similar thing here of graphing the regions that represent certain probabilities here. And next week, we'll come back and we will exactly come up with computations that, okay, I should back off on the word exact right there. We're going to see that getting exact areas underneath these curves is a little bit difficult, but there are some very good rules of thumb for estimating these the areas of interest here relatively closely. And that's exactly what we're going to be doing next week. So again, what I know is that on this graph, this represents 100% of all of the possible heights that a human could ever be. So the total area underneath the entire graph is 1, representing 100% of all possible heights of humans. What I want to do is indicate on my graph where I see events of interest and then maybe make a vague estimate of probability here. And so the probability first of interest is what is the probability that my son will grow up to be more than 2 standard deviations below average in height. So more than 2 standard deviations below average. Right? In this case right here, I can see that 2 standard deviations below average starts right there. And my question is, what is the probability that my son is more than 2 below average? In this case here, and I think, by the way, this is super important, notating these probabilities, I really care about your ability to do this, so you should be comfortable with the statements I'm making here. My math notation for this would be the probability that if x here is measuring the number of standard deviations from normal, then I am interested in the probability of that x value being less than or equal to, okay, I guess I said directly just more than 2 below average. So x is less than -2. I want to know the probability that my son's height, that the number of standard deviations that my son's height is away from average is less than -2, right? 2 or more below average is what we're looking at here. So again, what I can do, as I did before, is I could just shade this region of interest over here, right? So this would be like the area. And notice we really are accumulating essentially no area way out there in the tail, but we are getting like some area right there in this little region right here. And so maybe if we want to make like a vague estimate for this, a question that I might ask then is like, well, what's the area of just one of these little rectangles here? Let's just use this as our helper. Should notice that the width of this rectangle is 1 and that the height of this rectangle is 0.05. So it looks like one of these rectangles has area and therefore probability of 0.05. I might estimate that this to me looks like it's basically half of one rectangle. That makes about, and I'm very much ballparking this estimate wise right here. This looks to me about half of one rectangle, and we're technically picking up a little bit more area out here underneath this curve, but man, very little. Hopefully, you're down with the fact that not many people are between 4 and 5 standard deviations above or below average. That would be like being taller than 7 feet tall, or like shorter than like 4'6" as far as males go. There's just not a lot of people that fall into that category right there. So it looks to me like I can very much estimate my area here as about half of one rectangle. If one rectangle represents 5%, then this should be about maybe a 2.5% probability here. And by the way, we're going to confirm this number is pretty dang close to exactly a good estimate next week when we talk more specifically about our normal distribution. For today, I'm more interested in just the idea of area under the curve is the probability. So for question B, what is the probability that my son will grow up to be between half and 1.5 standard deviations above normal in height? So I can come up again to my graph. I'm interested in the probability of being between 1/2 and 1.5 standard deviations above normal in height. And so I can estimate for myself, what is this area of interest? Oh, by the way, I should mark this. That was problem A. Here's problem B. And now we might want to make like a vague estimate of like how many of these rectangles about do we think are in here. And notice, by the way, this is like half a rectangle and that's half a rectangle. So really this is like one whole rectangle here. So I'm seeing I've got for sure a 1, 2 of them, almost 3 of them. That one's missing a corner, but not much. Almost 4 of them. We're really missing one right about there. So we've got just shy of 4. That's about another half right there. So maybe 4.5. And then maybe another piece out there. This is about 5. This is very vaguely about 5 of these rectangles worth of area. And